Okay, so hello and welcome back. So in this video we will talk about voltage divider networks, and well, a voltage divider network is a bunch of resistors that you can put together in order to divide the voltage, right? It's basically, the name is self-descriptive. You're dividing the voltage. And you know that basically the voltage drop across basically when you have a bunch of resistors over here, for example, one resistor here, one resistor here, and so on and so forth. So if you connect this to a power supply, what happens is that the voltage will be, of course, divided here, because basically and the reason for that is that, for example, if I call this R1, R2, and R3, then at this point, for example, at this point between these 2 points, if I call this voltage V of R1, for example, this voltage would be the voltage drop across R1, right? So the voltage drop across R1 using the Ohm's law would be equal to V of R1 is equal to basically the current going through the circuit, which is basically essentially the V is equal to IR for the whole circuit. And for the whole circuit, you can the equivalent resistance is R1 plus R2 plus R3, so this R becomes R1 plus R2 plus R3, and there you have your I, and that would be V of S. So which means that the current going through the circuit is V of S divided by R1 plus R2 plus R3, right? So that is that. Now, the current going through the circuit is the current going through each of these resistors. And so the same current is going through R1. Now, the voltage across R1 would be V of R1, and is equal to, basically, V is equal to IR. That means that the current going through that resistor times the resistance of that resistor. So that would be basically V of S divided by R1 plus R2 plus R3 times basically the resistance of that resistor, which is R1. And then if you do this calculation for the rest of the circuit, you will find out that the voltage drop across basically across basically these two resistors, call it, for example, let's call this R2, across these two resistors would be V of R2, and not actually across R1, but you could call it, for example, I don't know, voltage 2, for example, because there is a distinction between that voltage and the other voltage, and that's basically one of the things that I was actually thinking about. But I cannot go down that path because I do not know really what electronics engineers do in this type of situation. But essentially, there is a voltage across this point and across this point in the circuit, meaning that, call it, for example, V of 2, which would be a voltage across these 2 points, not essentially across R2, but across R1 and R2 put together. And so then you would just simply you can say that V of 2 is going to be equal to basically V of S times R1 plus R2 R1 plus R2 divided by R1 plus R2 plus R3, which is the same thing as R1 plus R2 divided by R1 plus R2 plus R3 plus R3 times V of S. So that is V of 2. So we can actually write the voltage across R1 in the same way, meaning that R1 divided by R1 plus R2 plus R3. And I call this, for example, V of 1. I call this, for example, V of 1. And so V of 1 would be equal to R1 divided by R1 plus R2 plus R3 plus R3 times V of S. And by the same logic, V of 3, if I measure this voltage over here as V of 3 between these 2 points, I will get V of 3 is equal to basically R1 plus R2 plus R3 divided by R1 plus R2 plus R3 times V of S, which is the same thing as, so you can cancel all of this out with this, and so V of S is equal to V of 3 is equal to V of S, meaning that you're actually calculating the voltage across the power supply, meaning that V of 3 is actually the power supply voltage. So as you can see, V of 1 is a ratio of the power supply voltage. V of 2 is a ratio of the power supply voltage. V of 3 is, well, again, a ratio of the power supply voltage, although it's the whole power supply voltage in this case. And the ratio depends on the ratio of the resistors that you take in the circuit to the total resistance in the circuit in series, right? And then there is all kinds of constituent, and what I was thinking about is that, of course, you know that R1, for example, the voltage across R1 is going to be some voltage. The voltage across R2 is again going to be some voltage. And the voltage across R3 would be again some other voltage, and you could argue that basically V of, for example, R1 is equal to R1 over R1 plus R2 plus R3 divided by times V of S. That would be this ratio. And V of R2 would be equal to R2 divided by R1 plus R2 plus R3 times V of S. And the voltage across, and what I mean by V of R1 would be basically essentially only the voltage across, V of R1 would be basically the voltage across these 2 points. Exactly these 2 points. And then V of R2 would be the voltage across these 2 points, right? And then V of R3 would be the voltage across these 2 points. And then, of course, you can calculate them, and of course you can measure them in any circuit, in any similar circuit, that basically V of R3 also would be equal to basically R3 divided by R1 plus R2 plus R3 times V of S. That is also another way of basically dividing the voltage, but I have never actually used this myself in any circuit. I mean, in order to divide the voltage, to see what happens in that case. And moreover, I have never actually seen. I'm not really sure what electronics engineers do in this type of situation, or even if they do use it at all, because the problem is that this circuit is I mean, it's very, very important to understand what sort of resistor values to choose for this kind of circuit. Otherwise, then when you add some load to the circuit, then the whole circuit will change and all the voltages will essentially change. So it's not it's not the best way to divide the voltage, but that's basically one thing that usually you learn in basic electronics. So that's why I included this video here. Otherwise, and we will see what we can do with that, of course, in the future. It must be, of course, useful somewhere. And therefore, that's basically the whole story here. So that way you can basically calculate these voltages and put them together and so on and so forth. Now let's do a couple of examples here, 515, 516 and 517. Let's do a couple of examples here in order to work a little bit with these equations and with this kind of circuit, and then we'll see where that takes us. Okay, so now as a first example, let's say that you have basically so we have in a transistorized amplifier, the battery supplies 9 volts, right? So we have basically a transistorized amplifier, and the battery supplies 9 volts. So V of S is equal to 9.0 volts. Now the minus terminal is at common chassis ground, and at some point you need to get plus 2.5 volts, given an example of a pair of resistors that can be connected in series such that plus 2.5 volts will be provided at some point. So in this circuit, basically at some point you need to get a voltage of plus 2.5 volts, right? And the negative pole of your power supply is the chassis ground, meaning that you have basically your power supply over here. This is negative positive. This has been grounded in your circuit, and then at some point you need basically a 2.5 volts, meaning that you can connect this circuit to 2 resistors in series and connect this over here and call this, for example, R1, and call this, for example, R2. And for example, let's say that at this point you want to get a positive 2.5 volts. At this point you want to get a positive 2.5 volts, right? Now this over here is the schematic. Now of course there is many different combinations of resistances that can work here, and the way that you can do this is as follows. So there is one thing over here. There is one problem over here, or one fact over here that you need to be familiar with, and then once you know that, you can use that fact in order to basically find the values of your resistors. And that is basically the ratio of the resistor to the ratio of basically R1 to R. For example, if you wanted to get the 2.5 volt voltage at this point, which is essentially across R1 and this point over here, and this point over here, and I change colors, and at this point over here, right? So the plus 0.25 volts between these 2 points, right? So that is across R1. So this voltage is, call it for example V1. So V1 to basically call this V of S, which is equal to 9 volts and 9.0 volts. V1 to V of S is always equal to R1 to R1 to R of T, R1 to R of T, right? Because and the reason for that is that basically you know that basically this voltage over here across R1, V1 is the same thing as basically R1 to basically R1 plus R2 times V of S. That's just the ratio of the power supply voltage, right? So R1 plus R2, I can call it R of T, meaning that V of 1, I can call it R of 1 to R of T times V of S. Now if I take the ratio of V1 and V of S, what I will get is that basically V of 1 to V of S is equal to basically R1 is essentially equal to R1 times V of S divided by R of T, and then you can divide that by basically V of S, and V of S is equal to, well, you can just simply write V of S, and that would be the same thing as R1 times V of S divided by R of T times 1 over V of S. And V of S and V of S you can cancel out, you will get R1 by R of T, which means that basically V of 1 divided by V of S is equal to R1 divided by R of T. So you can use this fact here in order to find the value of these resistors. So now you know the ratio of the supply of the voltage that you want to get at this point to the supply voltage is 2.5 divided by 9. Is 2.5 volt divided by 9 volt, 9.0 volt. It's volt and volt you can cancel out. The voltage, the ratio becomes 2.5 to 9. And so you can choose the same ratio for R1 and R of T. But then your R of T has to be known, right? And since it has to be known, and since you have to choose some value for your R of T, so what you can do is that you take your R of T, which is equal to R1 plus R2, you take it as some value, for example, 1000 ohms, for example, 1 kilo. And this value is something that it has you essentially have to take many things into consideration into your circuit, and then you will based on experience and other factors, then you will choose some arbitrary value for this R of T. Doesn't matter what value that is. I mean, in a specific range, it doesn't really matter what value that is. So then you know that R of T is equal to 1000 ohms. So then you can say that basically based on this relationship, 2.5 divided by 9.0 is equal to basically R of T. We took that as 1000 ohms, and R1 would be equal to, basically you can cross multiply, you will get R1 is equal to basically 1000 times 2.5 divided by 9.0, which is equal to 225 and 2 zeros divided by 9.0, and that gives you basically something like, for example, 2500 divided by 9, which is equal to something about 277 two significant figures, 280 ohms, for example. We write it as 280 ohms, 280 ohms, and this, remember that this has two significant figures, so I write this as 2.8 into 10 raised to the power 2 ohms, for example. Usually in electronics we don't do that sort of thing, but well, in physics, in chemistry, in science, you have to specify the number of significant figures. And I just want to show that this number has two significant figures. And now that I know that my R1 has 280 ohms, so therefore, and I know that R of t is equal to R1 plus R2, then I can write 1000 is equal to R1, which is equal to 280 ohms. 280 ohms minus, and this is in ohms, plus R2, and therefore R2 would be equal to the 1000 ohms minus 280 ohms, which is equal to something about 720 ohms, R2. So that means that basically you have this resistor as basically you have this resistor as 280 ohms. You have a 280 ohm resistor here. You have a 720 ohm resistor here, and the voltage over here becomes 2.5 volts, and that's basically your voltage requirements in this circuit. But I mean, the numbers and everything is not that important. Important is to note the relationship between this voltage and the power supply voltage, which was basically V of 1, the voltage that you want to get over here. The ratio of that voltage to the power supply voltage is basically the value of the resistor to the total resistance in the circuit. And then using that fact, you will be able to calculate the value of your resistor. So that is basically one example here. Now, as another example for this type of circuit, what we can do is that is the following. Okay, so now suppose that you want to know in that circuit, in the circuit that we had before, that basically we had one resistor here and one resistor here, and was connected to some power supply, negative, positive, and this was R1, R2, and this was 280 ohm, and this was 720 ohm, and the power supply voltage is V of S is equal to 9.0 volts. 9.0 means you have two significant figures there, and these two resistors have also two significant figures. So what that means is that then your basically, if you want to know what sort of current is going through your circuit, and that is important because we, in the previous step, we said that when you choose these, you choose the value of these resistors arbitrarily, meaning that you don't really have to basically choose any sort of resistor, any specific type of any specific value of resistor, as long as you get the 2.5 volts over here, the plus 2.5 volts over here, then you're good to go. And this 2.5 volts just a you can get it through any ratio. That's just a ratio, and then as long as you keep that ratio, you will get the same voltage, meaning that multiply this resistor by 4, multiply this resistor by 4, you will get the same voltage over here, or divide this resistor by 4, divide this resistor also by 4, you will get the same voltage over there, right? But the problem is that once you multiply both of the resistors by 4, or divide both of the resistors by 3, for example, or by 4, or by 2, or by any factor for that matter, the total resistance in the circuit changes. Now, since the total resistance in the circuit changes and the power supply is kept constant, of course the current in the circuit changes, and then that current should be something that can be, of course, supplied by the power supply, and also that current should be something that can be handled by these two resistors, meaning that, of course, at the end of the day, some current is going through these two resistors, and the power dissipation capability of these two resistors have to be chosen accordingly as well, right? So that all of those things you already know. Which means that then you need to, for many different reasons, you need to know the current going through your circuit. Which brings us to the fact that basically then your resistors are basically your R of T in this circuit would be equal to R1 plus R2, which is equal to 1,000 ohms. And your V of S is equal to 9.0 volts. And therefore you know that V of S is equal to I times R of T. V is equal to IR. And therefore I is equal to V of S divided by R of T. And I is equal to V of S, which is equal to 9.0 volts divided by 1,000 ohms, which is equal to basically something about 0.0009 9,000th of an amp, or basically 9,000th of an amp, or you can say you can call it 9,000th, or to get two significant figures, you can call it 9.0090 amp, for example, right? Which you can call 9.0 milliamp, which you can call 9.0, for example, milliamp. 9.0 milliamp, right? So that means that basically 9 milliamp of current is going through this circuit now, and this 9 milliamp is going through both of these resistors. That means that then basically if you want to use what sort of resistors you need to use here, that would be P is equal to, for example, VI, and P would be equal to the voltage across this resistor, for example, would be basically across this resistor there is a voltage of 9 minus 2.5, which is equal to 6.5. So 6.5 volts times, for example, this current, and this is in volts, times this current 9.0 into 10 raised to the power negative 3 amps, which gives you basically 6.5 times 9 is equal to 65 times 9 at 1 decimal point there, so you get 45, and 9 times 6 is equal to 54 plus 4 is equal to 58, and 1 decimal points here, and then you can basically round that to 2 decimal places, meaning that you can call it, for example, 58 58 basically, 58 into 10 raised to the power negative 3 watts, which is equal to 58 milliwatts. So that means that you have, that means that your resistor has to be well, this number doesn't tell me much, so I have to write it as, for example, I have to write it as 0.058 watts, and that's 500th of a watt. That means that basically then you need to then you need to compare this, for example, with the range of resistors that you have. For example, you have normally you have 1/8 watt resistors, 1/4 watt resistors, you have 1/2 watt resistors, 1 watt resistors, you have 2 watt resistors, and so on and so forth. And then accordingly you can choose an appropriate resistor for that sort of basically situation, right? So that's basically one thing. So that is again another typical thing that you need to know about these things, about these circuits. And these are especially, I mean, these are all the basics that you know about electronics. Of course, when you want to design something and build something in electronics, then of course you'll either use these or you will have to learn some new things and so on. And so that's basically how the whole journey of electronics usually goes. So now let's do another example here, which is of course a good example. Okay, so now suppose that it is permissible to draw up to 100 milliamp of current in the problem that we had before, meaning that in this problem it's permissible to draw up to 100 milliamps, right? So which means that you have basically essentially two resistors here, and this is connected to a power supply, and this is the ground, and this is R1, for example, and R2. So the permissible current to draw is the permissible current in the circuit is equal to 100 milliamp, right? You want to design the circuit to draw this maximum current because that will offer the best voltage regulation for the circuit to be operated from the network or whatever. Now that's for whatever reason you want this current to be drawn by these two resistors basically in the network, both of them together. So now what you want to know what values of resistors you should choose so that 100 milliamps of current is drawn from this power supply, which supplies 9.0 volts, right? So of course it's very simple. Based on the current that has to be drawn by the resistors, you will calculate the total resistance of the circuit, meaning that you know that V is equal to basically the voltage is equal to I times R, and basically voltage is 9.0 volts. The current is basically 100 milliamps, so that's 100 into 10 raised to the power negative 3 amps times the resistance, which is well, the resistance. We want to calculate that. So your resistance would be basically 9.0 volts divided by 100 into 10 raised to the power negative 3 amps, which is the same thing as basically 0.09 0.09 into 10 raised to the power 3, 900 times 10 raised to the power 3, basically ohms, right? So then that means that you're basically, and to show that you have two significant figures here, you can actually, and supposing that this has 3 significant figures, you write that as 0.090 into 10 raised to the power negative 3 ohm, and that means that basically you have basically that would be basically 90 ohm, right? That would be basically 90 ohm. Now, and to show that basically this has two significant figures, again, you can write it as 9.0 into 10 ohm, for example. That you can also do. That's good practice if you get into the habit of specifying these. Your work would be much more scientific than just writing a bunch of numbers, right? So now you can, based on the 9 ohm resistor that you have, you can calculate the resistor, for example, the value of R1, meaning that basically you know that your R of t is equal to R1 plus R2, which is equal to 90 ohm. And we said that basically, if I call this the voltage across this point, if I call this voltage V1 is equal to positive 2.5 volts, that means that basically this voltage, the ratio of this voltage to the power supply voltage is the value of this resistor to the whole resistance, right? Which means that I can write V1 to V of S is equal to basically R1 to R of T, and R of T is equal to 90, so V of 1 is equal to 2.5 volts to basically 9.0 volts is equal to R1, which we want to calculate, to R of T, which is 90 ohm. And that means that basically then R1 would be equal to 90 times basically 2.5 divided by 9.0, and 90 divided by 9 is equal to 10, and 10 times 2.5 is equal to 25. That means that your R1 would be equal to 25 ohm, and based on that, then basically R2 would of course be 90 ohm minus 25 ohm, which is equal to 65 ohm. So that is basically how you would solve this type of problem. It's basically very simple, and well, all of these are required, of course, if you want to do I don't know, anything in electronics, and usually everybody needs a basic education for electronics, because today, I mean, our lives are primarily only electronics. I mean, from the very morning that you get up all the way up, whatever you do basically during the day, during your waking hours, even when at night when you sleep these days, everything in electronics, because your home is controlled by electronics, even your sleep is controlled by electronics, your heart is controlled by electronics, and so on and so forth. And so now I wanted to actually add something, but I forgot that. But essentially, these are the basic things that anybody needs to know about electronics. And anyway, most people take all of these courses in a basic physics course or in a basic university course or college course. But again, the goal of all of these videos that I'm doing here is that I want to basically do all of these videos, and then as a result of which we will be to enable us to be able to work on some basically radio circuits and power supply circuits and that sort of thing. That's the project that I am currently working on, and that's basically why I do all of these things. Okay, so I end this video here. In the next video we will do a couple of examples on different topics in electronics, and so I'll see you in the next video. Thank you.